Our star is not going to explode. The sun is nowhere near heavy enough to end as a supernova, and nothing about its death is sudden. Here's the actual schedule. In roughly 1 billion years, long before anything dramatic happens to the sun itself, its slow brightening strips Earth of a breathable atmosphere. Around 5 billion years from now, the core runs out of hydrogen. About 7.5 billion years from now, by the widely used model of Klaus-Peter Schroder and Robert Connon Smith, our star balloons to 256 times its present size, wider than Earth's orbit, and Mercury and Venus are gone. Then it sheds its outer body and leaves a cinder the size of this planet, cooling for longer than the universe has yet existed. No bang. A very long, very strange retirement. Start with the part almost everyone gets wrong, because the dangerous phase isn't the red giant. It's now. Helium ash piles up in the core contracts and heats, and fusion runs a little faster every million years. Our sun switched on at about 70% of its present brightness, and it is still climbing, roughly 10% more every billion years. Earth has a thermostat that has absorbed all of that. Rock weathering strips carbon dioxide from the air faster as the planet warms, cooling things back down, and the arrangement has held for 4 billion years. It cannot hold forever. Ken Caldeira and James Casting showed in a 1992 Nature paper that the same feedback eventually starves plants of the carbon dioxide they need. And in 2021, Kazumi Ozaki and Reinhard ran the system forward in Nature Geoscience with a coupled climate and biogeochemistry model. Their answer, Earth's oxygen-rich air has about 1 billion years left, give or take 140 million. And the sun will still look perfectly ordinary in the sky. So what's happening in there right now? Every second, the core fuses roughly 600 million tons of hydrogen into helium, and about 4 million tons of that mass stops being matter and departs as light. 5 billion years of fuel remain, and the models argue over that date by a few 100 million years either way. When the core hydrogen goes, the star doesn't switch off. It does something worse. The dead helium core, with nothing burning inside to hold it up, collapses under its own weight, and the squeeze ignites a shell of hydrogen around it. That shell burns fiercer than the old core ever did. The sun brightens, swells, and cools at the surface, drifting through the subgiant phase for hundreds of millions of years, going wrong far too slowly for anyone on a planet to notice. Then the climb turns steep. On the red giant branch, the burning shell eats outward, the core keeps compacting, and the envelope inflates the way a balloon does under a very patient pump. Schroder and Smith put the peak at a solar age of 12.17 billion years, at 256 times today's radius and 2,700 times today's brightness. Picture the distance from here to the sun, filled with star. Mercury is inside it. Venus too. And all the way up, a thick, slow wind peels the giant apart. The same study has it shedding 1/3 of its mass before it reaches the top. At the very top, our star does the most violent thing it will ever do, and from outside you'd barely notice. The core by then is degenerate, meaning electrons are packed so tightly that quantum mechanics rather than heat holds the center up. Degenerate matter has a nasty property. It gets hotter without expanding, so there's no safety valve. At 100 million degrees helium begins fusing into carbon, the temperature spikes, the spike accelerates the fusion, and the reaction runs away with itself. Astronomers call it the helium flash. For a few seconds, the core outshines a galaxy of ordinary stars. Essentially, none of it escapes. The energy goes into lifting the degeneracy, swallowed by the vast envelope overhead, and from a distance, the star just shrinks a little and settles. What follows is almost peaceful. Helium burning is stable, so the sun pulls back to around 10 times its current size and coasts there for 100 million years, smaller and hotter than the monster it briefly was. Then the helium runs out too, and the crisis repeats one layer up. A helium shell and a hydrogen shell now burn around an inert carbon and oxygen core, and the star heads back out along the asymptotic giant branch to around 150 times its present radius. This part is unstable. The shells can't keep time with each other, so every 100,000 years or so the helium shell detonates in a thermal pulse. The output lurches, the star briefly bloats past 175 times its present size, and each convulsion coughs another layer of gas into space. A few of those, and everything but the core is gone. Here the models start arguing. The pretty version of the ending is a planetary nebula. The exposed core, over 100,000 degrees at its surface, floods the escaping gas with ultraviolet and lights it into one of those glowing rings you've seen in telescope photographs. Schroder and Smith calculate that we don't get one. Our star sheds too much material too early, they argue, and finishes wrapped in a shell too thin to put on the usual show. But in 2018, Christophe Jasicki, Albert Zijlstra, and Marcelo Miller-Bertolami published a rival set of models in Nature Astronomy. In theirs, the dying core races to its peak temperature about 3 times faster than older work allowed. That's quick enough to light the gas before it drifts away. Their conclusion puts the sun right on the boundary, close to the lowest mass of star that can still light up its own cast-off gas. Ours glows in their models, but faintly. Which brings us to the question everybody actually asks. Does the sun eat the Earth? We don't know, and the reason is a tug of war between two effects that are close to evenly matched. As the giant sheds, mass its grip loosens and Earth's orbit drifts outward, which helps. But a bloated star raises enormous tides on its planets, and tidal drag hauls Earth back in, which doesn't. Schroder and Smith ran that contest in 2008 and found drag wins. Earth is engulfed just before the tip of the red giant branch, and a planet would need to start at least 15% further out than we are to survive. In 2026, Mats Esseldures, Stefan Matthijs and Leen de Sin redid the calculation in astronomy and astrophysics with newer tidal physics and got the opposite. Earth squeaks through. Their answer hinges on how fast the sun sheds mass late in life, and that rate is measured badly. High mass loss, Earth lives. Low mass loss, Earth is eaten. That's genuinely where the science sits. We do know what the swallowing looks like because we've caught one. In 2023, a team led by Kishileda reported in Nature the first live observation of a star consuming a planet, an outburst catalogued as ZTF SLRN 2020, 13,000 light-years away, seen as a slow infrared brightening and then a brief optical flare. A JWST follow-up led by Ryan Lau in 2025 complicated it. The host looks like an ordinary main-sequence star that hasn't swollen at all, so the planet probably spiraled inward on its own. Different cause, same result. What survives all this is small. The Sun's final act leaves a white dwarf of about half a solar mass, crushed into roughly the volume of Earth, so dense that a sugar cube of it would weigh a ton. Nothing fuses in there. It only radiates leftover heat into an emptying sky, and along the way, something rather lovely happens. The carbon and oxygen inside begin to crystallize. Pier-Emmanuel Tremblay's group used Gaia measurements of thousands of nearby white dwarfs in 2019 to catch that phase change in progress, visible as a pileup of stars stalled at the same point on the cooling track. The Sun will end as a crystal about the size of the world you're standing on. And then, the cooling never finishes. A white dwarf gone completely cold and dark is called a black dwarf, and the standard estimate says reaching that state takes on the order of 1,000 trillion years, tens of thousands of times the age of the universe. So there are none. Not one anywhere yet. The coldest white dwarfs anyone has found are still glowing at around 3,000 degrees, because the cosmos hasn't been running long enough for anything to finish dying. That's the real ending, and it beats an explosion. Our star will spend its next billion years making this planet uninhabitable, another 4 burning quietly through the rest of its hydrogen, a couple more swelling and shedding and coming apart at the seams, and then sit out there in the dark as a warm crystalline ember, running down a clock the universe is far too young to have started. The light on your face this afternoon is somewhere in the middle of that. It's the best part. Go and stand in it.